let's see. Hypothesis tests help us answer questions about preconceived notions we have or notions we have based on some prior facts. And it turns out a lot that we think we know, turns out there's not a lot of factual basis for it, but sometimes there is. Like we've been measuring human body temperature for a long time and we think it's 98.6, but is it really? Other questions I thought were interesting from reading this book and other books. Does sleeping with a light on affect weight gain? Okay, so there have been some studies on that. Are mosquitoes more attracted to beer drinkers than say someone who's hanging out drinking water? So if you're hanging out in the yard doing some social distancing get together and you're drinking water and your friend's drinking beer, are they going to get more mosquito bites than you do? So there have been studies on that, and perhaps we could take a look at that today or tomorrow. By average body temperature. Does one have a different heart rate during a quiz? So a lot of people have anxiety, and sometimes anxiety will raise your pulse rate, for example, maybe your blood pressure, your body temperature even. Some people are pretty calm when they're taking a quiz. Some people are more nervous in class than they are when they're taking a quiz. You know, people are different. So on average, do people have a different heart rate during a quiz? Some studies on that too we could take a look at. Do most math students read the book before doing the homework? For my research, the answer is unfortunately no. Hopefully you eventually read the book. Do most people take home their leftover box from a restaurant? I can think of how many times I've often forgot. It's like, damn, I wanted the rest of that. I forgot it at the restaurant. Good morning, April. Glad you could join us. So hypothesis tests can help us answer things like this. A question I brought up last week was in that syllabus quiz, I asked you how many hours of video stuff you watch each day on average, and I did a confidence interval for that. There's several studies I read on that, and one of them said the average American watches 5 hours of television a day on average, which just like blew me away. So the question I had, well, do students watch less than average? And how can I measure that and answer that question? And that's what hypothesis tests help us with. Okay, so now we just got to get used to the language of hypothesis tests and then the procedure for running through them. So a hypothesis test is a lot like a science lab where we have to run through this procedure and we get some results and then we explain what those results mean. So there's going to be a lot of writing in this section. And if you're doing the homework and not writing this stuff down, then you're doing yourself a disservice. So please, please, please take notes on every single problem. Write down stuff. And I'll give an example of that today. All right, so if you have something you're testing, that means that there's some kind of claim. And claims can be based on past knowledge or new beliefs. And those beliefs are often based on some observation someone made. So for example, claim, average body temperature is about 98.6, but I think it's lower. Why do I think it's lower? Well, the first reason I think it's lower is my temperature is almost always, if I'm healthy, like and I'm not sick, is almost always lower. Okay, but you know that's okay. I'm not an average person. Nobody is really. And then you know I've measured my family and I've measured friends and I've seen some studies and data that it looks like it's actually lower than 98.6. And there was some data back on the confidence interval page about this and so we made a confidence interval for body temperature, and it turned out 98.6 often wasn't in that confidence interval, which is weird because we say it's 98.6. So how do the claims work here? So when we have claims, something you want to distinguish between is there an equals in the claim? And you might care, like, who cares if there's an equals in the claim? And is there an equals here? Well, I see the word is, and is in English language is often associated with equals in mathematics. Here I'm talking about an average of a population, so that would be the symbol mu. That's a population average. So mu here would be the average body temp of humans. So we're going to define our variables. Average body temp, degrees Fahrenheit of humans. And the claim up here basically states, let's switch colors for fun, that that average equals 98.6 degrees Fahrenheit. Anytime there's a statement that we can derive an equals from, this is part of what we call a null hypothesis. So a null hypothesis always has an equals in it. Okay. So possible other null hypotheses would be something like, so other examples. Maybe somebody claims that some like average heart rate of healthy adults is less than or equal to 80 beats per minute. Since this has an or equal to, it's got an equals in it, this would have to be a null hypothesis. If somebody said that average grades in some class are generally greater than or equal to 65%, right? Since there's an or equal to, this would have to be a null hypothesis. So this is, again, super, super, super important to help get your hypotheses straight when you're making a test. A null hypothesis has to have an equal sign in it. Okay. Now, so a null hypothesis is like some previous belief. So null means nothing. So if I had nothing else to go on but what somebody told me, this is what it would be. Okay. So null again means nothing. It's a belief based on no other new information. Okay. So then we have an alternative hypothesis, and an alternative hypothesis is usually based on new information. So oops, I don't want that yet. Let's continue with this example. So again, with this example, we got body temp. And I'm saying we have a thing called a null hypothesis, usually pronounced hypothesis, but I need to say it that way to spell it right. And our null hypothesis is that the average is 98.6 degrees Fahrenheit. If you have a null and you're considering, is it really true, then maybe you have an alternative hypothesis. So we have to have an alternative if we want to do a test, otherwise there's nothing to test. So alternative hypothesis, and chime in with a question if I go too fast or you're concerned. Hypothesis is just some other belief. And so my claim was, I think it's less. So my alternative hypothesis, that's supposed to be a mu, would be that mu is less than 98.6 degrees Fahrenheit. And something that's important about the alternative hypothesis is the alternative can never have an equals in it. Alternative can never have an equals in it. So other possible alternative hypothesis would be something like, well, I just don't believe it's 98.6. So I would say it's not equal to 98.6. And this is not equal. It's not an equal sign. So that would be an acceptable alternative. Or somebody might say, I'm always hot, right? And so they might say, nah, I think average human body temperature is greater than 98.6 degrees Fahrenheit. But you cannot have an equal sign. So, so kind of summarizing that, new page, the null hypothesis versus the alternative. A null can have in it an equal to, or a less than or equal to, or a greater than or equal to. An alternative could have and these don't necessarily go together, it just kind of depends. It could have a not equal, it could have a greater than, and it can have a less than. Often we kind of pair them up like this, but it doesn't have to be this way. For example, in the body temperature example I'm about to do, I'm saying my null is, I'm saying my null is this one, and my alternative is that one. Okay? But sometimes people will pair, if somebody gives the alternative, they'll choose that for the null. And there's just different philosophies about that, and it's not a big deal for us. But the big deal is a null hypothesis must have an equal, and an alternative hypothesis cannot have an equals in it. Then we have some special notation that goes with it. So if I go back over here, math people are lazy and they like to write as few words as possible. So instead of writing null hypothesis is this and alternative hypothesis is that, we might state it a little bit different. So let's put it down here. So if I just put this in strictly in math terms, and H means hypothesis with a little subscript 0, that means that's the null hypothesis right there. So null means nothing, and often 0 means nothing. And then we put a little colon next, right? 2 dots, colon, and then we state what the hypothesis is. So you have to have some population parameter, which for us is either a mean or a proportion, some kind of equal to statement, and then the number. So in this case, the null hypothesis is mu equals 98.6. And I like to put the units here too, but some people don't put it there. And then the alternative hypothesis, sometimes that's an H with an A for alternative, but sometimes people put an H with a 1, right? 0 versus 1. So there's different ways people write it. Okay, I usually put an A there. And so my alternative would be mu is less than 98.6 degrees Fahrenheit. And there'll be a couple of questions where you have to distinguish this notation. And on the application, you're going to have to actually type this out. And later I'll show how to type that on a computer. So again, null hypothesis, H0, alternative hypothesis is either H with a subscript A or H with a subscript 1. All right, so we have some notation. We have this idea of a null hypothesis, which is usually some previous idea about a situation. And we have an alternative hypothesis, which is often some new information. A claim could either be a null hypothesis or an alternative hypothesis. It depends on the presence of an equal sign in the claim. So example of that, so here I had the claim that average body temperature is 98.6. So that was the null. If somebody else made a different claim, like let's say claim average heart rate of ICU patients is greater than 90 beats per minute. Okay. So if somebody made that claim, since this does not have an equals in it, so in math notation, it's an average, so I use mu, they say greater than, and then they say 90. This would have to be an alternative hypothesis. So I would say that would be an HA. What could the null be? So options for the null, it just kind of depends. Options for null, if that was the claim I was going on, if I wanted to run a hypothesis test, I could say that the null hypothesis, so H0 null hypothesis, that mu is 90. That would be an acceptable null hypothesis. Or some people would go with the opposite of greater than, and the opposite of greater than would be less than or equal to. It's supposed to be a 0 down there. Better. Sorry, I write sloppy when I get excited. Mu is less than or equal to 90. Okay. So sometimes when you're given a situation, the claim might be an alternative hypothesis, and other times it's the null hypothesis. And then how do you pick the other one? Well, sometimes you just say, I'm going to do this one, right? It's just kind of, you just go for it. Other times it might be based on the data that you have. Like you went to the ICU and you randomly selected some patients and you're like, wow, their beats per minute seems to be higher than the average person. In which case that would lead us to say this would be the alternative. Why would not be an equals? What's the problem with equals? Okay, so that's a good question. What is the problem with equals? think that's your question, Mindy. Is the problem with equals? Am I getting at the heart of your question there, or am I off track? Okay. So here's the problem with equals. Equals is a fact. Not a hypothesis. A hypothesis is an educated guess. Educated guess. Theory. Okay. Now in math, theories are mathematically proven, and math though is an artificial world. It doesn't truly exist the way we conceive it. It's just this weird thing in our brain. Then there's reality, and in reality we have a lot of theories about the way things work around us, and our theories they work, right? But they're often just an approximation of reality. They're not exactly. And with hypothesis testing, we are basing an opinion on data. And I'm writing that today. Opinion on data. What's data? Data is a sample. A sample is not the whole population. So we never know for sure what the truth is because we don't have the whole population. And I'm going to get more into this as we progress here. We don't have whole population. So I could have a representative sample, but it could be just a little off from what the truth about the population is. And we're never going to know what the truth about the population is. It's always just an educated guess based on the data. So we can never know that something is for sure. We can have a belief that something is greater or less, but we can't say is. Think about the whole confidence interval thing, right? On average, there's a window of human body temperature that's healthy. If you're too low, if your body temperature is too low, you're going to die, right? Hypothermia. If it's too high, then you're going to die from overheating or from whatever illness is affecting you. So there's this range of temperatures that humans can survive safely in, right? But the average, a particular number, is not true for everybody. It's just, you know, we kind of narrow down all this vast variety we have and try to nail it with one number. So for most situations, you can't say one number is it. And even when we're trying to nail an average about something, we can never know the average for sure. There's always a chance we're wrong. So because of that, we can never say something is or equal to a particular value. It's just impossible because we never have the whole population. If we did have the data for a whole population, then there's no point on using sample data to guess. Okay, and so that's kind of the broad idea of why equals is a problem. And then the data either supports, so let's take a look at that next. Not ready for the new claim. So let's look at the body temperature one still, body temp. And I have a null hypothesis to 0 that the average is 98.6. And I have an alternative hypothesis. Pen, write me an A, please. Close enough. That it is less than 98.6. And if we looked at kind of a distribution from a sample of human body temperatures, what we're going to find if we smooth out the histogram, that it's going to be this roughly normal looking curve. Now, not all populations have these symmetric normal distributions. Most don't. Human body temperature is roughly normal. 98.6 is in the middle. Now, I'm not looking at the temperature of an individual. I'm looking at the temperature of a group of people. So this is an average, mu. And so maybe I have some sample size like n equals, I don't know, 200 people. And what we're going to find is that majority of people, their average body temperature is somewhere between, let's put it, let's see, 98.6, 97-ish over here. And let's go out to around 100-ish over here. That's roughly in the middle there. We're going to find that most people fall in this category over here. Most groups of people fall in this category over here. And then we run some sample, right? So this is, let's say, a sampling distribution. It's actually, we'll write it both ways. You still got to get used to this phrase, sampling distribution. What the hell is a sampling distribution? In this case, it would be a distribution graph of sample means. So that's what I have here roughly in blue. Let's erase this red for a sec. Put it over here. So then I run some sample, n equals 200 people. And I find the average of that sample, x bar, right? Not the population, but x bar. Let's suppose I find that to be 97.2. That would be about over here. If this right here is my like 95% range of what we usually find, and only 5% is unusual, right? 2.5% live out here of samples, and 2.5% live out here, then finding a sample that's in here, that's normal. So this sample would support the null hypothesis. Get that right? Close enough. So what does that mean? Well, yeah, it's less, but it's not a lot less. If I find an average human body temperature of 200 people to be 96, I'd be like, whoa, that's way out here. That's weird. It's supposed to be 98.6, huh? So either these are weird people or 98.6 is wrong. So either the sample is close enough to what was preconceived or it's farther away, which means either the sample is bad or the assumption is bad, right? And so we'll talk about which one is bad and what the risks are of making those conclusions.
So how would you find the p-value in a problem like this?
Let's do it. What the hell? Okay, so my first goal here was to, sections 1 and section 2 are about the theory, and then and then I skip a section, I think, and then section 4, if I remember the order of these right, and 5 is more about doing hypothesis tests. So I'll come back. I had some other examples about claims, which is which, and then the probability of making an error. So remember those contingency tables we made before? Those are things we need to look at. So let's do a situation. Let's do the human body temperature one. Show desktop. So I'm going to move over to stat key here if you want to join me. I'm going to draw some pictures to go with this. All right, so we are jumping away from confidence intervals for the moment and looking at hypothesis tests, and I'm looking at a mean. So we'll either do a mean or a proportion, although I may do some differences in means later, just for examples. And okay, they have a body temperature example. That's the first one that comes up. So they have a sample of 50 people, and that is roughly normal. There's someone that has a temperature way out there. There's an individual that has a temperature way out there. So we can't do a hypothesis test based on a single sample. We need thousands of samples. So that's what the software does for us. So whenever we do a hypothesis test, the things we have to get straight first are, do we have the right data set? Check. Do we have the right null hypothesis? And my null was mu is 98.6. Check. Once I'm sure about the data and the null, then I start generating samples. Because what this does here, it doesn't matter what the mean of the sample is at the moment. Assuming that 98.6 is the correct human average, it uses this sample to regenerate other similar samples, believing that 98.6 is correct, regardless of the mean, whatever the mean was there. So it's a little more complicated than a confidence interval. So we need to get at least 6,000 samples like before. Okay. Then what we need to do is, the idea, a p-value, I better write this down because it's complicated. Come on, where's my notes? There we go. Let's go back. So we're getting ahead of where I wanted to be, but that's okay. So here's the question. How do we decide to accept the alternative hypothesis? And a lot of statisticians would cringe at me using that notation. So I'll explain in just a sec. So how do we decide to accept the alternative hypothesis? The correct way to phrase that for most statisticians would be how they're kind of logically equivalent. How do we decide to reject, oops, missed some letters there. There we go. The alternative, the null hypothesis. So if we reject the null hypothesis, that gives us the opportunity to accept the alternative hypothesis as the new belief. And so what we need to do is we need to then find a data set or find some samples, usually you want more than one, whose means, in this case we're talking about means, are sufficiently far away from the null. So whenever we have a null hypothesis, right, we assume the null hypothesis is true. And then we look at the data. So in this case, I'm just going to squeeze a little drawing off to the side here. If we look at our distribution of sampling means, so again, this is the sampling distribution of sampling means, we believe 98.6 should be in the middle. So we build our sampling distribution, and then we have that 95% in the middle, say, kind of like with confidence intervals. If our data shows up over here, right? So this is X bar from the sample. That's way in the unusual range over here. So this is the unusually high range. Oops, I went the wrong way, didn't I? I'm supposed to go the other direction. Instead of erasing, all right, over here. Okay, so that was our sample mean, X bar. The chance of getting something like that sample or less, this is again unusually low. Why? You can only judge something to be low or high if you have a belief of what it should have been, right? So we believed it should have been 98.6 for the average. We found a sample that's way lower. So that means one of two things. Either the sample is screwy, right? We got some kind of biased sample, or the belief about 98.6 is wrong. One of those two things has got to be wrong. So we assume the null hypothesis is true. If we find a sample that's sufficiently far away and we have a good representative sample, then we have evidence against the null that, ooh, man, that 98.6 can't be right. And we have, let's see, what I was going to write now. Assume the null is true, and we have a, damn it, Gary. Oh, good representative sample, yep. Representative. Then we can reject the null. Okay, so this is a long story. This probability out here is the p-value, and it's based on the data. So to calculate a p-value, and this is all written up, by the way, nice and neat with an example on the home page for week 7. We'll do it stat key. Come on, internet, move along, please. Let's see, has anyone else joined us? Doesn't look like it. Week 7. Model hypothesis test for means with stat key. So I walked through the whole procedure there, which is what I'm working on here. All right, so I got my data in there, I set my mean, I run tons of samples. Once I do that, if I only want the p-value, which is what most researchers go for these days, then they just enter their value. So the p-value is always based on the sample. My sample has a mean over here of 98.26, right there. That is below the expected mean, so I'm going to do a left tail. If that was above the expected mean, I would do a right tail, and a two tail is more complicated. We'll talk about that later. So I'm going to go for a left tail here, and then I come down here on that left side and I type in the sample mean, which was 98.26, and it says, okay, based on 98.6 being the belief as what the average should have been, the probability of getting another sample with a mean of this or smaller is 0.0005. Okay, so I'm going to copy that into my notebook here, and I think I might need a new page for that. Yep, new page, screenshot. So and I'll redraw this too. Current page. Okay, so here's the stat key evidence based on the sample. And reminder about a few things on this page. This right here is the null hypothesis, which is the value of the population, that's mu. This number over here, let's make that green, that's from the sample data. And this red region right here is the chance of getting, the probability of getting other samples that are less than. So this number right here is the p-value. Okay, so I'm going to write down the p-value in a couple of ways here. First, if I write the p-value in probability notation that we were working on a couple weeks ago, it would be the probability that some other sample it has a mean that is less than or equal to our mean, 98.26, knowing that the population should have been 98.6. So it's a conditional probability. So in language that my mom might get, it would be the probability. Oh, come on, pen. Again. Probability. Oops, too many. Probability, there we go, of finding another sample and on your homework, you're going to mostly just care if you're just trying to get points about getting that p-value and not what it means. But I need to understand what it means, otherwise you're not going to be able to do the application. So the probability of finding another sample with a smaller mean, and it's smaller because I'm doing my alternative hypothesis was a less than. Probability of finding another sample with a smaller mean when we were expecting a mean of 98.6. So the key of a p-value is we're expecting whatever the null hypothesis says, we're expecting that to happen. If our sample ends up too far away and it's a good representative sample, then we have some evidence that the null hypothesis is incorrect, okay? So in this case, because I have a small p-value, that implies that my decision, is to reject the null hypothesis. And the decision is either reject or fail to reject. We never accept the null, we just say the data seems to support the null, or the data does not support the null. And we accept the alternative as a default to having data that doesn't represent what was previously believed. So it's kind of sketchy language there, but that's the way we talk about it. So since the p-value is a very small number, the decision is to reject the null hypothesis. And then there's a conclusion I would write up. And so the conclusion would look something like this. There is sufficient evidence to reject, and there's more human ways to write this. I'm kind of doing an in-between way. To reject the hypothesis that average human body temperature is 98.6. Average and then I might say the data supports that it's less. Okay. Does my data support that the average is 98.26? The answer is, well, that's what the sample said, but I don't know if that's the population mean. Think about a confidence interval. Confidence interval gives us this window. So if somebody said, well, give me an estimate on human body, a new estimate on human body temperature, so then I would have to run a confidence interval instead. So all the hypothesis does says either the previously known information is supported by the data or it's not supported. If it's supported, we fail to reject the null hypothesis. If it's not supported, then we reject the null hypothesis. Okay, question here. So you're saying with this information that the average is less. Yeah, this sample indicates that average human body temperature is less. So if the people that conducted this survey, that the data is represented here at StatKey, so here's the data table. If this is a good representative sample, then this shows that human body temperature on average is less than 98.6. Right? Does this show that human body temperature on average is 98.26? The answer is no. But we would have to run a confidence interval to give an estimate with a margin of error, which I haven't done here.